All right, here we go. Section 9.2, tests about a proportion. I'm going to do this one a little bit differently. The PowerPoints that I have are not working right, and I don't know exactly why. So this is straight out of your textbook, but I'm going to talk through parts of it and hopefully make things clear. So you can follow along on this video. You can obviously follow along or reread things on your text as well, because this is straight out of the textbook. But with explanation, so hopefully that will make it okay. Right? 9.2, tests about a population proportion. Back in section 9.1, there was this made-up example about what if somebody claims they're an 80% free throw shooter, but we think maybe they're not. And so what we did is we would say, all right, let's go down to the gym. I'm going to have you shoot 50 free throws and we'll see. Now, we would not expect that they're going to make exactly 80%. They're not going to make 40 out of every 50. An 80% free throw shooter in the long run is going to make 80% of the shots. Does it mean they're going to make 40 out of every 50? Of course not. So the way this was set up in the example back in 9.1, their one p hat, the one time they did this, they got 32 out of 50. In other words, they got 64%. Now you might say, see, 64 isn't 80, so obviously you're a lying liar. Well, what we know about sampling variability says, even if you're an 80% free throw shooter, you're not going to get 80 every time. So is 64 so far out there that we go, dang, that's crazy? Or is it go, yeah, we would expect that. So we get to this thing called a hypothesis test. 9.2 is going to be about the specifics of when we're working with p's and p hats. Mu's and x bars will be in section 9.3. So the way we talked about setting up the hypotheses in section 9.1, the null hypothesis is the true proportion really is 80%. We say, you know what? We believe you. It's always, always, always going to be about the true mean or proportion, in this case proportion. The true mean, the true proportion really is 80%, but we're suspicious. The alternate is that, hey, maybe it's a little bit less than that, or maybe it's something different than that. And we have to tell our reader, hey, that P that we're talking about, that's the actual free throw percentage in this case. Okay, so the first thing we have to do is we have to check our conditions. And you know what they're going to be. They haven't changed. They're going to be the same as they've been before. Randomness, it says SRS. Normality, n times p, and n times 1 minus p, both being bigger than 10. Notice it's n times p and n, not n times p hat. Okay? N times p and n times, those have to be both bigger than 10. Independence. This one's a little bit goofy because they were talking about a computer generator shooting free throws. This would be the 10% condition. Well, guess what? 50 free throws is less than 10%, less than or equal to 10% of the infinite number of free throws that could be taken. So, randomness, normality, and independence. Randomness will be stated, normality, n times p and n times 1 minus p. Independence will be the 10% condition. Just a side note here, normality for proportions. The central limit theorem only works with means, not proportions. N times p and n times 1 minus p is our only chance in proportion problems. The central limit theorem will be in 9.3. It will be with when we're talking about means. So there's this thing called the sampling distribution. It says, you know what? Let's assume the null hypothesis, that p is really 80%. Let's assume that's true. Now, what we learned in Chapter 7 about sampling distributions says if the real mean is 0.8, the real proportion is 0.8, then when we go out and find p hats, sometimes we're going to get 0.8, sometimes we're going to get like 0.81, sometimes we're going to get 0.79. We're going to get a lot of them. This is the sampling distribution. There is an almost infinite number of dots in this picture, and every one of them represents a different p hat that could have happened. But wait, we found a p hat, and it was right down here at 0.64. 0.64 is the p hat that happened. Now what we have to do is say, wait a second, if that's what p hat, our p hat was, where does that fit in with this world in which we built it on the fact or the idea, or the assumption at least, that it's really 80%. Is this surprising or not? Now, 0.64. I'm going to show you something that you won't actually have to do because your calculator knows how to do this, but I want you to know what your calculator is doing. So, and this straddles a couple pages on your book, so I'm just kind of scrolling here. This 0.64 on a normal curve with a center at 0.8, that thing has a z-score. Except we're not really calling it a z-score right now, we're calling it a test statistic. We're saying, where does that statistic that we found in our test, where does that fit in with the sampling distribution that was created from our null hypothesis? What it is, for all practical purposes, the z-score. So it says, hey, 0.64 minus 0.8 divided by the standard deviation. That's the thing called the test statistic, and it will be called z. Now, the reason we do that is so you could go and you could look on table A to find out what is the area out here in this part of the tail with that z-score, with that test statistic. What this says is if we expected them to make 80%, they would have been around here. When they went out and got 64%, that has a z-score of negative 2.83. That is 2.83 standard deviations below what I would have expected. That's pretty out there. The question is, what is that area? That area is found by looking on table A, but we're not going to do that. We're going to do that on your calculator. So here's your calculator. I just showed you from the book how you would find the test statistic and how you would then use that to go and find the p-value. What chance would I be there? Your calculator knows all about this. You would go to Stat, and you would scoot over to Tests. We are going to do a thing called a one-prop z-test. We took one proportion, and we are doing a z, test statistic, to perform a hypothesis test on that, a one-prop, one proportion z-test. So when I click on that, my calculator is going to ask for a few things. P sub 0. This is the proportion that we built our null hypothesis on. In this case, it was 0.8. 80% is what was in the null hypothesis. X is how many people said yes to your question. How many free throws did you make? In our simulation, our shooter made 32 out of 50 shots. X is how many said yes, how many shots they made. N is how many they shot. How many people did we ask our question? Now, the prop here, this is from the alternate hypothesis. In the alternate hypothesis, we were suspicious that our proportion was less than the null proportion, the 80%. So I'm going to pick this one. Now you can click Calculate, but I'm going to show you why you want to click Draw. Here's what my calculator just did. It said, hey, I'm going to build a world in which I'm going to call this 0 because it's standardized. This says this is what the sampling distribution would have looked like for an 80% free throw shooter. And it's hard to tell, but it's shaded down here at negative 2.8284. Does that sound familiar? That's like negative 2.83. It says our guy shot 32 out of 50. That's 64%. That has a z-score, a test statistic of negative 2.8284. That's the z-score. That's the test statistic. That has a p-value of 0.0023. That's a tiny number. And if the p is low, then we're going to need to reject the null hypothesis. So we're going to pause your calculator and go back to the book. Back here. This is the same thing that it looked like on my calculator, right? A test statistic of negative 2.83 and the p-value of 0.0023. So what do we do with that? The shaded area is the p-value. That's a tiny number. That means 0.2% of the time that's going to happen. So in terms of what we do with our null and alternate hypothesis, that would tell me the p is low. So I would say, you know what, there is almost no chance that this is true. So I would reject the null hypothesis, and I would say something like, so I have pretty good evidence that their free throw percentage really is less than 80. I would reject the null, and I would have strong evidence in favor of the alternate that their true proportion is really less than 80. That whole process is called a one-sample z-test for proportion. So here's going to be the template for doing one of these, for every one of these. State, plan, do, conclude. I will tell you right now that when you get to the test for Chapter 9, you're going to have to do one proportion test, and you're going to have a state, plan, do, conclude. You will also have one mean test, but we'll talk about that in section 9.3. State, what are the hypotheses, and at what significance level? Where is that alpha? Where is the line where I say, you know, if the p is lower than this is where I'm going to reject or not? And then what parameters are you using? You're saying, oh, where p is the true free throw percentage or whatever. Plan is we're going to state what we're doing, or we're going to tell what the test is going to be and check the conditions, randomness, normality, independence. Do, if we meet the conditions, we're going to do the calculations. Now, it says here, compute the test statistic, then go find the p-value. When you do the test, it will tell you what the test statistic was, what was the z-score for your p-hat, and what's the p-value. And then in conclusion, you're going to say, I either reject the null hypothesis, so I have evidence of my alternate, or I failed to reject my null hypothesis, and so I don't have evidence in support of the alternate. Okay? So, here, these are the two types of situations we're going to be in this video. And I'll go through another example in just a second. There will be a null hypothesis that the true proportion is some number that they tell us. Here's the formula for finding the test statistic, which you won't have to do because of your calculator. All it says is take your p-hat minus the one that was stated over the standard deviation. Well, that's finding the z-score. Your alternate hypothesis is going to be either, hey, the alternate is really bigger than that, or the alternate is really smaller than that. If it's bigger than that, we're talking about up here. If it's smaller than that, we're talking down here. These two are called one-tailed tests because we're only looking on one tail of the normal curve. In the next video, we'll talk about this situation. If the null hypothesis says, hey, I think somebody says their free throw percentage is 80. I don't know if I think it's higher or lower. I just don't think it's 80. I'm going to say not equal to. That would be a two-tailed test because I don't know where it is. I'm just saying I think you're out there somewhere in one of those tails. In any case, it has to be normal for this to work. If the normal condition doesn't work, or if the population isn't less than or equal to 10% of the, if the sample isn't less than 10 or equal to 10% of the population, we got to do something different. Statisticians can do different things. It's just not what's in this test. So here's the one more example. And I'm going to talk you through the example. I'm going to show you this is a template for your answer on all the assignments on your test. I'm going to talk you through the template for your answer, and I'm also going to show you how to do it on your calculator. So this was referred to in section 9.1. We didn't talk about it in the video. It's in your text, so I'm sure most everyone read it. But it says, you know what, if you're a potato chip producer, you get truckloads of potatoes. What they've decided, and you can read more about this, but in section 9.1, what they've decided is if they have a truckload that comes in and there's more than 8% of those of those potatoes are bad from that truckload, we're sending that truck back. We're not even going to accept it because we don't want bad potato chips. 8% we can live with. Less than 8% is awesome. More than 8%, that's a problem. And so what we have to do, we don't have time to check every single potato. So the supervisor, in quality control, selects a random sample of 500 potatoes, and they see what percent of those are blemished. And then if it's over 8%, then we go, that makes me suspicious. So they do a hypothesis test. Just because we get 8.1%, the truck driver is going to go, wait a minute, maybe you just got a bad sample. Or just because we got 7.9% might be, who knows, maybe we just got lucky. So we do a hypothesis test because we know even if that truckload is 8% blemished, doesn't mean every sample is going to be exactly 8%. So we're going to do this. 47 potatoes said, yes, I'm blemished, out of the 500 potatoes that we asked, right, that we checked. Before we start, we say alpha is 0.10, 10%. This is our line where we're going to go if this is a low p-value or a high p-value. So we'll talk about that when we get there. But just remember, before we even started the test, they said 10%. Usually it's going to be 5. This time they said 10. So 47 out of 500, I don't know what that is. That's 9.4%, I guess. Right? So they think, oh, that must be a problem. The truck driver says, wait, maybe that was just a bad sample. So state, we want to perform a test at the alpha equals 10% significant level. Again, if the problem doesn't tell you what the significance level is, you're going to use 5%. It says the null hypothesis is, hey, P is really 8%. That truckload of potatoes is really only 8% blemished. We believe them. But our suspicion, our alternate hypothesis, is that P is bigger than 8%. Hey, what was P again? Oh yeah, P is the actual proportion of blemished potatoes. So our plan, if the conditions are met, we're going to do a one sample z-test. You can call it a one prop z-test for the population proportion. Randomness, it says it was a random sample. Normality, 500 times 0.08 is 40. 500 times 1 minus 0.08 is, those are both bigger than 10. We've got a normal curve. Independence, because we are sampling without replacement, we took 500 potatoes. Is it safe to assume there are at least 5,000 potatoes in a shipment? I think so. We tell our reader, we're assuming there's more than 5,000 in there. So the do portion of it, this is where your calculator is going to come in. Darren showed, his do shows the actual calculations. And I'm going to walk you through them quickly, and then I'm going over to our calculator. It says, if it was really 8%, I would expect this. Most of the time we'd be around here. Sometimes we'd be down here. Sometimes we're up here. When we got that 9.4%, 47 divided by 500, 9.4%, that's above average. What the heck? 9.4% minus 8% divided by this big old formula, P times 1 minus P over N. That says, you know what? That 9.4%, that's a z-score of 1.15 standard deviations above average. That's an above average thing from what I would expect if this was really 0.08. So then Darren says, hey, let's look it up on table A. Pause. Now remember, 47 potatoes were blemished, 500 were sampled. And so we'll go over to our calculator. Still got this in there from the previous problem. So we go stat, scoot over to tests, down to one prop z-test. In the book, Darren calls it a one sample z-test. Same thing. The null hypothesis. It was 0.8 because we were talking about an 80% free throw shooter. Now 0.08. Be really careful about that, right? We know that you got to be 0.8 does not mean 8%. So be careful. 47 potatoes were blemished out of the 500 that I sampled. Now, this time, I'm not suspicious that my true proportion is something different than 8%. I'm not suspicious that my proportion is something less than 8%. I'm suspicious that the true proportion is something greater than 8%. And so, I asked my calculator to draw the picture, and it says, oops, what happened? That was an actual mistake, but I'm going to pretend I did it on purpose to illustrate something. I just said greater than, but I didn't actually click on it, so it stayed on less than. So make sure that you actually click on the one that you mean. If you recall, I went over there and I said we want this one, but I didn't click on it. And so obviously we get a picture that looks like this. I would have expected to be in here. My sample of 9.4% is 1.15 standard deviations above the mean. My test statistic, that has a p-value of 12.43%. If I have a load of potatoes that's 80% blemished, 12% of the time, I'm going to get a sample like this that's 9.4% blemished, right? That can happen. So we have to ask ourselves, is this p-value low? Go back to the calculator, or go back to the book. Notice, by calculating the test statistic and looking on table A, Darren found the same p-value that we got, 12.5%. So here's what we do. We say, wait a second. That p is not low compared to alpha. If the p is low, reject the null hypothesis. But this p is not low. So I would, and here's the way I do it, I say I would fail to reject. It is not low enough to reject. I don't accept the null hypothesis, but I fail to reject it. And I say, sorry, nope. I don't have enough evidence right there to send that truck back. Here's the notation that Darren would say. Since our p-value is greater than the chosen significance level, since it's not low, we fail to reject. And we say, there is not enough evidence to conclude the alternate hypothesis, and therefore we keep that load of potatoes. And we go, maybe it was just a weird sample. Okay? That's the idea of a one-tailed test for proportions. State, plan, do, conclude. State has the hypotheses in it. Plan, check your conditions, randomness, normality, independent. Do is where Darren says you're going to do these. So if you look in the back of the book, you're going to see all this stuff. We're doing it on your calculator. Go to Stat, scoot over to Tests, one prop z-test, tell it what you want, have it draw the picture, take that test statistic and p-value, and then make a conclusion about your hypotheses. You either reject the null hypothesis or you fail to reject the null hypothesis. And therefore, we either have evidence in support of the alternate or we do not. Those are the choices.